We've already talked a little bit about how we can use a sample to estimate characteristics about a population. So let's just review really quickly that when we have a population, but the population is too big or spread out or inaccessible in some way for us to survey everyone. Therefore, what we do is we take a random selection, so we'll put here random selection of people or subjects, whatever's in the population, of people from the population. We randomly select those in order to create our sample. Now, what we're interested in is some parameter value for the population. And this could simply be a proportion of the population, a population proportion. It could be the mean, it could be the standard deviation, but there's some characteristic about the population that we want to find. But since we can't ask everybody, we take a random selection in order to get our sample. And then for the sample, we calculate what's called a statistic, which again could be a proportion for the sample. It could be the mean, the standard deviation, but some characteristic of the sample. So we call characteristics of the sample statistics, and we call characteristics of the population parameters. And then our goal here is to use what we learned about the statistic to make an inference about the parameter. In other words, maybe we find the sample mean, and we want to use what we know about the sample mean to then make an inference about the population mean, the corresponding population parameter. This is the general process that we're going through. So let's, for example, talk about the population proportion. When we talk about the proportion, we're just talking about the number of subjects in our population or our sample that meet a certain criteria. So when we say population proportion, we're talking about the number of people in the population that meet a certain criteria. For instance, if we want to know how many students in our school have brown hair, then the population proportion, which we call P, will be the number of students in our school with brown hair divided by the total number of students in our school. But let's say that there are 5,000 students in our school. And so because there are so many, we're not going to be able to survey every single one of them to see exactly how many students in the population have brown hair. In that case, we might take a random selection of 100 students to get a sample, and then survey just those to see how many of them have brown hair. What we'll get is the sample proportion, the proportion of students in the sample with brown hair, and we call the sample proportion P hat. Here's the thing though, if we take a sample of 100 students, and then we count the number of those 100 who have brown hair, we might get a value of, let's say, 60. So we would say 60 divided by the 100 students in our sample is 0.6. And so we get a value for P hat of 0.6, and the sample proportion is 0.6. But then let's say we take a different sample of 100 students, and 48 of them have brown hair. In that case, for that sample, we would say P hat is 0.48. And then maybe we take a third sample of 100 students, and we find that P hat is 0.71. 71 of the 100 students had brown hair. The point is that every time we take a sample, we may get a different value for P hat. The sample proportion is going to be different. So the question then is, if we're always going to get a different value for P hat, how do we use our value for P hat to make an inference or estimate the value of the population proportion P? Well, what we do is we take more and more samples, and as we take those samples, we're going to come up with lots and lots of values for P hat. Well, when we take all of those values for P hat and we consider them all together, what we're going to get is the sample distribution of the sample proportion, because this is the sample proportion here. So we're getting lots and lots of values for the sample proportion, and those values are going to create a probability distribution, sample distribution, that we can use to answer probability questions about P hat and therefore about P. The amazing thing is that if we do this right, the sampling distribution of the sample proportion is actually going to be a normal distribution. However, in order for the sample distribution of the sample proportion to be normal, we have to meet a few conditions. So the first one is that the sample needs to be random. So we need to have a random sample. And we saw up here that we did a random selection of people to get the sample from the population. That has to be true. The sample needs to be random. The second thing is what's called the normal condition. And the normal condition says that we have to have at least 10 successes and at least 10 failures in our sample. So what do we mean by successes and failures? Well, like in this example, we're looking for the proportion of students with brown hair. So we could call having brown hair a success and not having brown hair a failure. And so what we want to say then is that when we multiply the number of students in our sample, n, by the population proportion, p, that we're going to get at least 10. So this says we get at least 10 successes. The number of students in the sample multiplied by the probability of failure, 1 minus p, also has to be greater than 10, so that we get at least 10 failures. Now, sometimes in the problems you'll be asked to solve, you'll be given the population proportion, in which case you can use it in these formulas. If you don't know the population proportion, then that probably means you're working with just one sample, and you'll use that sample proportion in place of the population proportion. So for instance here, if this was our single sample, we had calculated a sample proportion of 0.6, then we would take 0.6 times 100 to get 60. That would show us that we're getting 60 successes, which is greater than 10, so that checks out. And then we would take 100 students in the sample, n, times 1 minus 0.6, or 100 times 0.4, and we would see that we're getting 40 failures. That's also greater than or equal to 10, so we're good there. We would have met the normal condition. So we just have to check those two. And then lastly, we need to satisfy the independence condition. The independence condition tells us that our samples need to be independent, and that can happen in one of two ways. If we are sampling with replacement, then automatically our samples are independent. If we're sampling without replacement, for example, we're asking students as they leave the building at the end of the school day, then we're sampling without replacement. And if that's the case, that's okay as long as we are keeping our samples under 10% of the total population. So our total population is 5,000 students, and 10% of that is 500 students. So if we're sampling without replacement, then the largest sample size we can take is 500 students. But since our 100 student samples are underneath that threshold, then we can still get away with sampling without replacement because that 10% threshold is actually going to approximate independence for us. So in this case, we've met the three conditions for normality: random sample, normal condition, independence condition, which you can remember is also called the 10% rule. Then if those three things are true, that means that the sample distribution of the sample proportion is going to be approximately normal. So because we have an approximately normal distribution, that means that we can identify here in the center of the distribution the mean of the sample proportions. And the amazing thing is that this is actually going to be equal to the population proportion, p. We're also going to be able to find the standard deviation of the sample proportion, which, because it's the standard deviation for the sample, we oftentimes call it the standard error of the proportion. And that standard error formula is going to be sigma is equal to, and then the square root of the population proportion times 1 minus the population proportion divided by the number of subjects in our sample. Now keep in mind that for some problems, you're going to have the population proportion p, in which case you'll want to use that. But other times, you're not going to have the population proportion, and in that case, you can substitute the sample proportion p hat for this population proportion p. So let's go through an example. Let's say that we have an ice cream shop that claims that 40% of their 1,000 daily customers purchase a waffle cone with their ice cream. You decide that you want to verify this claim, so you're going to take a simple random sample of 90 of their customers, And what you'd like to know is the probability that the sample proportion, the proportion of people in your 90% sample who buy a waffle cone, is going to be within 5% of their claim of 40%. So, like we talked about before, the first thing we want to do is verify normality. So we want to look at our three conditions. Well, the first is random sample, and we were told that we took a random sample. So we're kind of assuming that. So we have met that condition. The second is the normal condition. Are we going to have at least 10 successes and at least 10 failures? Well, we're taking a sample of 90, and we've been told that the population proportion is 40%. So NP will be 90 times 0.4, and that's 36, and that is in fact greater than or equal to 10, so we will have at least 10 successes. And then N times 1 minus P will be equal to our sample size 90 multiplied by 1 minus the population proportion 0.4, and that's 0.6. So 90 times 0.6 is 54, and that is also greater than or equal to 10, so we will have at least 10 failures. So we have met the normal condition. And then the independence condition, we're not sampling with replacement, we're just asking 90 customers who come out of the store. However, our 90-person sample is underneath the 10% threshold because 90 divided by the total number of customers, 1,000, is equal to 9%. So because we've stayed under this 10% threshold, we can assume independence, and therefore we've met the independence condition as well. So now we can go about the business of answering the probability question now that we've verified normality. The first thing we want to do is find the mean of the sample proportion. But we know that the mean of the sample proportion is going to be equal to the population proportion. So we can say that the mean of the sample proportion will also be 0.4. Then our standard deviation is going to be equal to, we have the formula over here, the population proportion, so square root 0.4 times 1 minus 0.4, which is 0.6. In other words, here in the numerator, we have the probability of success multiplied by the probability of failure. And then in the denominator, we have n, which is the size of the sample, and our sample size was 90. If we calculate that value, we get 0.0516, and now we have mean and standard deviation of the sample proportion. Our question is, what's the probability that the sample proportion is going to be within 5% of the population proportion? Well, if we sketch here our mean, we know that the mean is 0.4. So let's say this is 0.4. And then we want to know the probability that we're within 5% of that. Well, 5% is 0.05. So within 5% would be between 0.45 on the high end and 0.35 on the low end. So we're really asking, what's the probability that we fall within this interval? Well, we know that the standard deviation is 0.0516, just a little bit more than that 0.05 distance we're talking about. So what we want to do is express this 5% value, the 0.05 value, in terms of standard deviations. So we would take 0.05 and we divide that by our standard deviation, 0.0516. And what we get is approximately 0.97 when we calculate this fraction, which means that this value here of 0.05 that gets us from the mean up to 0.45, or that gets us from the mean down to 0.35, it's about 0.97 of a standard deviation. So it's almost one full standard deviation, but not quite. But now that we have this in terms of standard deviations, we can actually look this up in a z-table to figure out our probability. So we're really looking for the probability that we stay within negative 0.97 and positive 0.97 in our z-table. Now, if we look up positive 0.97 in our z-table, we get a value of 0.8340. And if we look up a value of negative 0.97 in our z-table, we get 0.1660, which really means that the probability that we are less than positive 0.97 is all of this area here, and that probability is 0.8340. But then the probability that we're less than 0.35, which is a z-score of negative 0.97, is 0.1660. So this probability right here, up to this point, is 0.1660. So what we want to do is we want to subtract the 0.1660 from the 0.8340 to just give us this value in the middle right here. The result then of that difference is 0.668, or if we round to the nearest hundredth, we get approximately 67%, 0.67 or 67%. In other words, what this tells us is that there's an approximately 67% chance that the sample proportion p hat of any 90-person random sample we take is going to fall within 5% of the population proportion p. In other words, given this particular sampling method, we have about a 67% chance of being within 5% of the ice cream shop's claim.